Good evening everyone. My name is Renu Raman Sahu and today we will be discussing some of the assignment questions of week 9 and some of the previous year questions as well. So let us go to the first question. So what the question is asking, for the zero field 1D Ising model, which of the following is correct representation of entropy, the specific heat, the free energy and the average energy respectively. So the way to, so here so it is quite a bit of lengthy calculation which of which I will tell you the process. So first you have to calculate the entropy. First you have to calculate the partition function. So once you obtain the partition function for 1D Ising model, or this is the partition function. For 1D Ising model. So this can be found by something called transfer matrix method, and there are some other methods as well which is available in the literature that you can look up, or there are so this is kind of an involved calculation. So once you have this the expression of this, what you can do now is you can calculate the free energy F as minus kBT log of the partition function. Then you can get so once you get the partition function, you can calculate all these quantities and they will turn out to, so the free energy is given as minus kBT log of the partition function. So this is how you get this free energy. Then you need to calculate the average energy. The average energy E, this is given as minus 2 by dou beta del beta of log Z, where beta is 1 over kVt. Then what you can, so this is how you will get the average energy, the free energy. Now to get the specific heat, what you need to do, you have to do the derivative with respect to temperature of the average energy. So this is how you get the specific heat. And for the entropy, what you need to do is you have to use this thermodynamic relation. So the thermodynamic relation that you have to use is F is equal to E minus Ts. Okay, this is the expression for the Helmholtz free energy in terms of the internal energy, temperature and entropy. So basically S you will get E minus F over T. Okay, and then once you obtain this, you can plot this in any plotting software, and what you will get is, so I'll tell you what you will get is just a second. Okay, no one else has time. So for the free energy, so if you start plotting, what you get is this expression. For the free energy, you will get F is equal to A. So this is the expression for the free energy. And then for the average energy, you will get the average energy. This is the average energy, and this is this, when you do the derivative of this with respect to the temperature, you will get this as specific heat. and from and then this is the entropy. Okay, so you have to follow this method. So this is the method. You have to the hard work is just to calculate how you do the partition function. Just a second. So in the last week also we had discussed a similar problem. There we have outlined how we calculate the partition function z. It is available in the lecture also that you can look up. Okay, so basically what you get is, so this would be your answer. Okay, so now let us go to the next question. So it is asking what is the partition function of a 1D ferromagnet J greater than 0. So J greater than 0, it represents it represents ferromagnet. Why? Because see, the system wants to minimize the energy, and it is minus sign is already there and J is positive. So this quantity has to be positive so that this energy is lowered. So for this to be positive, see, and the spins sigma I and sigma j, they can take only plus or minus 1. So if sigma I is 1 or the upspin, then this also has to be upspin, so that it is 1 1, 1 into 1 is 1. Or if this is downspin, then this also has to be downspin. So minus 1 into minus 1 is 1. So this is basically positive, and that multiplied with this minus, that will give a negative energy. So the negative energy means the lowering of the energy, and lower the energy, more stable it is. So here the stable system is the ferromagnet. So what this Hamiltonian will allow is parallel alignment of the spins. So that is why we call it a ferromagnetic Hamiltonian. Okay, and J has to be greater. If J is equal to if J is greater than 0, then we call it a ferromagnetic Hamiltonian. Okay, so now for a 4-spin system with periodic boundary condition. So what does that mean? That means that H is equal to minus J sigma Ij, this sigma I sigma j. Let us try to expand this. So it is minus J, this sigma 1 sigma 2 plus, so this angular bracket, it represents nearest neighbor interactions. So sigma 2 sigma 3 plus sigma 3 sigma 4 plus sigma 4, and since it is a periodic boundary condition, this 4, the nearest neighbor of 4 is one is sigma 3 and sigma 1. So this is your required Hamiltonian. Okay, now what you have to do? So you have to calculate the energy. So you have to calculate various energies. So that energy comes from different combinations of this sigma 1, sigma 2, sigma 3, sigma 4. Okay, now this sigma 1, it can take values 1 and minus 1, sigma 2 can take 1 minus 1, sigma 3 can take 1 minus 1, sigma 4 can take 1 and minus 1. So what you do is, so there would be how many possible values? So it has 2 values, it has also 2 values, 1 and minus 1. So it is 2 to the power 4 2 to the power 4 different values you will get, or 2 to the power 4 different combinations of the sigma i's. Okay, so how do you do that? So you write 1 minus 1, 1 minus 1, 1 minus 1. So 2 to the power 4 is 16. So you make, you can do that serial number. This is 1, 2, 3, so on up to, you make it till 16. You write 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1 like this. So and then again you 1, 1, minus 1, minus 1. So up to this 16. Then you 1, 1, 1, 1, then minus 1, minus 1, minus 1, minus 1, and then next 1, 1, 1, 1, minus 1, minus 1. And for this 16 times you 8 times 1 and 8 times minus 1. Okay, this is how you do, and from there you can calculate what is this product, sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 4. From there you calculate this product, and once you calculate that product, so this is what, this is your energy values, right? Then you have to calculate e to the power minus beta h, or the energy. So there you will get 16 such values. You have to sum over all those 16 values. Okay, you have to sum over all those 16 values. This is how you calculate your partition function. So what you can do is, so here I have made a column to make it easy for you. So see, sigma 4, it is 1 minus 1 1 minus 1 1 minus 1. So there are 16 such values. Okay, then here it is 1 1 minus 1 minus 1 1 1 minus 1 minus 1. Then here it is 4 ones 4 minus 1. So then you have to calculate this quantity, sigma 1 into sigma 2. So that is what that was in the Hamiltonian, and you can see here it is just 4. The rest, this becomes 0, this is 4. You just have to calculate these values. Okay, now what you have to do, so this we have h is equal to what, minus j times this sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 4 plus sigma 4 sigma 1. This is what we have. Now we want partition function, right? So we have to do e to the power minus beta into so if you multiply, you have to multiply with minus 4j. Okay, so here if you multiply with minus j, it becomes 0 only. So you have to multiply this with minus j, multiply this with minus j, multiply this with minus j. So this will be e to the power minus beta minus 4j. Then this would be e to the power anything 0, it is just 1. So 1 1 1. So 4 ones, and again e to the power minus beta, now it is plus 4j. Then again it is 1 1 1 1. Then e to the power minus beta, and it is plus 4j. Then again 1 1 1 1, and e to the power beta minus beta, it is minus 4j. So it is minus 4j. So this, if you add all of this, what you get, so let us see how many ones, 1 2 3 4 5 6 7 8 9 10 11 12. So it is 12 plus, so this you can write what, so e to the power, so if you add these two, what you get, 2 cos hyperbolic 4 beta j, right? And if you add these two, you get the same, 2 cos hyperbolic 4 beta j, and if you add them, what you get is 4 cos hyperbolic 4 beta j. So this is your partition function. Okay, so your correct answer would be 12 plus 4 cos hyperbolic 4 beta j. I hope you understood this question, how to solve this. Now let us go to the next question. Okay, the Langevin function L alpha is represented by, so this is a widely known function in the literature, and it is just given by, so you can just you will come across it in different situations. You just have to remember that this is given by L of alpha is equal to cot hyperbolic alpha minus 1 over alpha. Okay, now what we need to do, so this is a widely known function, and it is given by this formula. So this is your correct answer. You just have to look this up. Okay, now here is an interesting question. The Hamiltonian of two interacting particles, one with spin 1 and other with spin half. So let's say that S1 is a particle 1, one is spin half, spin 1. That means if the spin operator, so S1 square, if operates on this particle, let's say this particle is 1, then what will be the then what you will get is 1 h bar square 1 into 1 plus 1 of 1. So this will be your eigenvalue. Okay, and as if particle 2 is a spin half particle. Okay, so s2 square operating on the particle 2, so this is spin 2, or this you can write as s2 square. So s is equal to half, this is spin 2 particle, and just this 2 is just a level. Okay, so this will give you h bar square 1 by 2 plus 1 into so this is your eigenvalue for s2 square operator. Okay. Okay, so now what we are going to do is we have to find the largest eigenvalue of this Hamiltonian. Okay, so let us now do that. So the Hamiltonian H is given by a s1 dot s2 plus b s1x plus s2x. Okay, so now so if I want to do s1x of the particle 1, so this s1x can have 3 different eigenvalues. Okay, because the total spin is 1, the eigenvalue of this can be h bar times 1 or h bar times 0 or h bar times minus 1. So the 3 possible s1 eigenstates of this can be 1, 0, minus 1. And for this s2x, this can be plus half or minus half. Okay, so we want to maximize it, so we'll write plus half. Okay, and for this so there can be 3 possible values, 1, minus 1 and 0 for eigenvalue of s1x. Okay, so this is what we get. For the, if you want to maximize, we have to use this. Now let us look at this quantity. This quantity, how do we find? So if we add the spin angular momentum s1 plus s2 to get s, so this is the operator equation. Now what we do is we drew the dot product of the same s2 s1 dot plus s2, we do the dot product, and this is s1 s into s, which is s square. So what we get is s square is equal to s1 square plus s2 square plus s1 dot s2 plus s2 dot s1. Okay, and since these are acting on 2 different particles, so s1 and s2 they commute. So what we will get is s1 square plus s2 square plus 2 s1 s2. This will be like this. Okay, now up to this is an operator equation. Now we will replace this by its eigenvalues. So okay, now we know that this is spin 1 particle and this is spin half particle, and on addition, what is the maximum value this s can take? So this s can take values from 1 plus half to 1 minus half. Okay, so for maximum value we have to take 3 by 2. This is the value it will take. So the eigenvalue equation will be 3 by 2 to 3 by 2 plus 1 is equal to, what is s1 square? S1 square will give you this is spin 1 particle, so 1 into 1 plus 1. Then s2 square is what? So it is half into half plus 1 plus s1 dot s2. Okay, so this gives me what? So this will give me the maximum value of s1 dot s2. Okay, so it will be s1 dot s2 is equal to 15 by 4 minus 3 by 4 minus 2 into 1 by 2. So 15 minus 3 is 12. 12 by 4 is 3. 3 minus 2 is 1. So what you get is 1 by 2. Okay. So the maximum value of s1 dot s2 you obtained is this much. Now all we need to do is to replace all these values. So let us do that. So what we have here is h is equal to a s1 dot s2. So we have h is equal to a s1 dot s2 plus b s1x plus s2x. Okay, we just now got that this will be a, and so what we will get here is, so if you so if we would have done correctly, so it is there would be a factor of h bar square in everything, h bar square, h bar square. So this would have been h bar square. Okay, and here so it will be h bar square by 2 plus b so this also will have h bar square. So this is h bar times 1 plus h bar times 1 by 2. So what we have is, so for the maximum eigenvalue, so this is a h bar square by 2 plus 3 by 2 b h bar. So what you have is 1 by 2 a h bar square plus 3 b h bar. So your correct answer will be this one. Okay, so now let us go to the next question. From the mean field solution of Ising model, the leading order contribution to the magnetization M from the magnetic field H at critical temperature Tc is Zj. Okay, so the way we approach this problem is we have to start from the self-consistent equation of the Ising model. The self-consistent equation of the Ising model, it is given by self-consistent equation for magnetization. For Ising model. This is given by m is equal to tan hyperbolic beta jzm plus h Okay, now what we want to do, we have to invert this. Tan hyperbolic inverse m is equal to beta j z m plus beta h. Okay, now here you see this, what you have is uh, Tc you can write as z j over kb, you multiply this t up and down, so what you have is z j beta t. So what you can write this as, so beta zj can be written as Tc over t. So beta zj is Tc over t, Tc over t into m plus beta h. Okay, now we are going to expand this in the limit m goes to 0. So this we can approximate as m plus m cube over 3 plus some higher order terms which we are neglecting. This is equal to Tc over t into m plus beta h. Okay, so now what we are going to do, see this m, the linear term in m that we can take together, m1 minus Tc over t plus m cube by 3 is equal to beta h. So h will do, and here we will multiply kbt. Okay, now at the critical temperature, so at the critical temperature means when T becomes Tc. Okay, when T becomes Tc, what would happen? So this quantity will, so T will approach Tc, and this quantity will approach 1, and 1 minus 1, this will approach to 0. So we will be left with kBT m cube over 3 is equal to h in the limit where temperature is at the critical temperature. Now from here we can see that m cube is directly proportional to h, which means that m is proportional to h over 1 over 3. So your correct answer will be h over 1 by 3. Now let us go to the next question. Okay, the variation of susceptibility chi with temperature T for an Ising model in the mean field theory. So we already saw that in the from the self-consistent equation, H is given as, so this is the equation that we already got. So I'll just highlight. So this equation we already got. We have to start from this equation. So H is equal to kBT m. So this is kBT m1 minus Tc by T plus m cube by 3. Okay, this is your expression for H. Now all you need to do is to find susceptibility. So chi is given as limit m tends to 0 m here. So this is your expression for the susceptibility, magnetic susceptibility. So all you have to do is you have to take derivative of this expression with respect to m. So what you will get is kbt minus tc over t plus m cube by 3, so it is m square. Okay, and so this is, if this is your chi, if you do so what is this? It is the derivative of h with respect to m, so this is actually your 1 over chi. So this means 1 over chi is equal to dou h over dou m. Okay, so basically chi is equal to 1 over kbt 1 minus tc by t plus m square, and you have to take that in the limit of m going to 0. Okay, so what you have to take is, so this will give you 1 over kb t minus tc. Okay, so what we have is chi is directly proportional to t minus tc to the power minus 1. Okay, so your correct answer is minus 1, which is this. Now let us go to the next question. The Hamiltonian of 3 Ising spins S1, S2 and S3 is taking values plus or minus 1 is. So what we have is, so this is again we have to do it in the similar way as we did the previous question, one of the previous question. So let us try to do that. So we have to, so what we have to do, the procedure is to first take all the possible values of spin. So how do you get all the values of spin? So there are 3 values, S1, S2 and S3. So 2 to the power 3, it is 8. So there will be 8 values. So we'll enumerate all the values S1, S2, S3. Okay, so this will be 1, 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1. So it is 1, 2, 3, 4, 5, 6, 7, 8. 8 values are there. Then you have to do 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1. Then 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1. Now we have to calculate what is the value of h for all this all these rows. So for this one, h will be what? Minus h minus 2j. For this it will be just this will be plus h, then this will be, so you just have to put these values in here and you have to obtain. So it is minus h plus 2j, then plus h, then again minus h, then plus h plus 2j, and this is minus h, and this is plus h minus 2j. Now we have to calculate the partition function. So here what we have to find? We have to find the mean value of S3 in equilibrium. Okay. So how do you find the mean value of S3? So we have to find so S3, the average value is given by So we have to count each of, so the all of this 3 can be all of this 8 are the possible ways of the energy configurations. So if we want to find the mean value, so let us start from this state, this particular state. So it is 1 times the probability of this state is e to the power minus beta times minus h minus 2j over the partition function. Okay, so that is the contribution of spin from this part. Then again plus 1 times e to the power minus beta h over z. So that is the contribution from this part. Then from this part we have to take plus 1 times e to the power minus beta minus h plus 2j over z. Then the contribution from this. So it is plus 1 times e to the power minus beta h. Now what over z? We have to find what z is also. Okay, then we have to take minus 1, so plus of minus 1 times, so this is the first minus 1, right? So what we have to do for this, e to the power minus beta into minus h, so which is basically beta h over z, then plus e to the power minus beta, plus again this minus 1 we have to multiply, and this minus 1, and the energy of that state is minus beta h plus 2j over z. Then we have to do minus 1 e to the power beta h over z plus minus 1 e to the power minus beta h minus 2j. Okay, now let us find what is z. So this we have to again simplify. We have to take some terms common, and we have to take some terms common, and then we have to evaluate or to simplify. So let us first simplify the partition function. So partition function will be e to the power, you see there are 4, so z equal to, so you see e to the power beta h, there are two terms, e to the power beta h and 2 to the power minus beta h, so it will be 2 times e to the power beta h plus e to the power minus beta h. So these 4 terms are taken care of. Now we have to take e to the power minus beta h, so let us take these 2 terms plus e to the power minus beta h plus e to the power, so e to the power minus beta h, if we take common from here, what we have in bracket is e to the power minus 2 beta j plus e to the power 2 beta j. Then we have to take care of this term. Okay, so minus beta, so it will be e to the power beta h e to the power minus 2 beta j plus e to the power minus 2 beta j. Okay, so now we can take these 2 common, so this you can write as cos hyperbolic 2 beta j, and then you can take these 2 terms common. So what we will get is So we'll get the partition function equal to, so from the first term what we can take, 2 times e to the power beta h plus e to the power minus beta h. We took this common, and and we're going to replace this as, so e to the power 2 beta j and e to the power minus 2 beta j as 2 cos hyperbolic beta j. So we are going to replace this cos hyperbolic 2 beta j is equal to e to the power 2 beta j plus e to the power minus 2 beta j. So on using that, what we have is cos hyperbolic 2 beta j plus 1. Okay, now we can further simplify this as, so this you can write as 2 times 2 cos hyperbolic beta h, and this you can write cos hyperbolic 2 beta j plus 1. So what you have is 4 cos hyperbolic beta h cos hyperbolic 2 beta j plus 1. Okay, so now let us look at the numerator of this. So numerator of this term, so the numerator is given by, or that is basically your spin, expectation of the spin is equal to 1 over z times, so I'll just write down the terms. So if you just follow, you can follow from this expression here. So it will be e to the power minus beta h minus e to the power, so I'm just rearranging this so that it is easy to understand what is how the calculation is going on. Minus beta h minus e to the power beta h plus e to the power beta h e to the power 2 beta j plus e to the power minus 2 beta j minus e to the power minus beta h e to the power 2 beta j plus e to the power minus 2 beta j. Okay, and then we have to put the bracket. So this you can write as minus 2 hyperbolic sine hyperbolic beta h, and there are two of these terms, so it will be 1 over z, so it will be minus 4 sine hyperbolic beta h plus, so and this will be 2 cos hyperbolic 2 beta j into plus, I'll just write 2 sine hyperbolic beta h 2 cos hyperbolic 2 beta j. Now what we have is this, we can take common as 4 sine hyperbolic beta h, 4 sine hyperbolic beta h, this we took common, and we are left with 2 cos hyperbolic 2 beta j minus 1. Divided by the partition function. Now we can write the expression of partition function underneath. So it is 4 cos hyperbolic beta h, and what we have here is so there would be no 2 here because we have taken the 4 common out, so these 2 will not be there. This is cos hyperbolic 2 beta j plus 1. So this 4 cancels this 4. We have tan hyperbolic beta h. Now what we have here is, so this cos hyperbolic 2 beta j, that you can write as, so e to the power 2 beta j plus e to the power minus 2 beta j. So minus 1 it is there, so it is, there would be a division by 2. So you multiply the numerator and denominator by 2. So all you have is e to the power 2 beta j plus e to the power minus 2 beta j plus 2 this. So this you can write as tan hyperbolic beta h, and you see the numerator you can write as e to the power beta j, so this is beta j plus e to the power minus beta j whole square divided by e to the power beta j, oh, so there has to be minus, it is this is minus e to the power beta j plus e to the power minus beta j to the power whole square. So now you see this can be written as sine hyperbolic, and this is tan cos hyperbolic. So it is tan hyperbolic beta h into tan hyperbolic square beta j. So this is your average value of S3. This is S3. So your correct answer is option 4. Now let us go to the 8th question. All you have to do here is to so here I will tell you just one how to solve this, and then what we can do is and then we can go to the next question. So I will tell you how to calculate for one term at least. Yeah, so we have this operator. So the operator is half minus s1z half minus s2z. So if you just simplify this, it is 1 by 4 minus 1 by 2 s1z plus s2z plus s1z s2z. This is your overall operator. Now if this operator works on let us say the first one is, so let us try to do that. One by 4 minus by 2 s1z plus s2z plus s1z s2z. This we want to operate on up, spin up. The first particle in up, spin up, the second particle is spin down. So for the up spin, so let us try to do that. So the first term is just 1 by 4 times the same state. For the second term, what we get is, it is 1 by 2. So when S1Z operates on this, it will just operate on the first operator. So what you will get is H bar times 1 by 2. So it is just, since it is a spin up, so we'll get plus half. And the eigenvalue will be actually h bar half. Then when this operates on the spin down, it will be minus h bar by 2. So this term will vanish, plus, so we have to use these expressions. Okay, so there is no h bar, so we just have to write plus half and minus half. So it is and we have to write pen and okay. Then it is what, let us look at this operator. So when S1Z will operate on this, we will get plus half, and S2Z spin down, it is minus half, and this will always be the eigenvalue. So what we get is, this plus half cancels minus half, and this plus 1 by 4 will be cancelled by minus 1 by 4. So effectively you get 0. Similarly you have to do for the rest of the problems. Yeah, so now we can do this, the similar exercise for the others as well. So it is quite obvious that for this also we will get 0 only. So let us try to do for this up operator. So 1 by 4 minus 1 by 2 s1z plus s2z plus s1z s2z, this operator acting on up. So since now all these eigenvalues, since both are up, you will get half and half for all these operations. So it is 1 by 4 minus 1 by 2, 1 by 2 plus 1 by 2 plus 1 by 2 into 1 by 2. This is up, up. So what you get here is 1 by 4 plus 1 by 4, which is just 1 by 2, and this is half plus half is 1, so it is minus 1 by 2. So what you got here is for up operator also you are getting 0. So there would be this, so either this is the answer or this is the answer. So let us try the other one as well. So 1 by 4 minus 1 by 2 s1z plus s2z s2z plus s1z s2z s2z. This one is acting on down operator, and what we are getting is 1 by 4 minus 1 by 2 minus 1 by 2 minus 1 by 2 plus minus 1 by 2 into minus 1 by 2 down. So what we get here is this is 1 by 4 plus 1 by 4, it is 1 by 2, and this thing is 1 by 4 1 by 2, and this minus minus cancels, this will be 1 by 2, half of is 1, so all you get is this, and the coefficient is 1. So this is your correct option will be this. Now let us go to the next question. Which of the following is correct? So we have to write where s plus and we have to express this s square as a function of s plus and s minus. So what is s plus? S plus is xx plus I sy, and s minus is sx minus I sy. So let us calculate this quantity. This is equal to sx plus I xy sx minus I xy. Okay, so what it will give me is sx square plus I minus I sy square plus I sy sx minus sx sy. So what we have here is sx square plus sy square plus I, this is commutation of sy sx. Okay, so we know that this commutation sx sy is equal to I s z. So what we have is sx square plus sy square, and we know that sy sx is equal to minus of sx sy is equal to minus I s z. So plus I, and this is minus I s z. So what we have is sx square plus sy square plus sz, because minus I square is 1. Now from here, from the question, we have s x square plus sy square equal to s square minus sz square. You just write that this is s square minus sz square plus sz. So s square is equal to, and this is what, s plus s minus. Now we just have to rearrange s plus s minus plus sz square minus sz. This is your expression for, this is your correct expression. So it is plus sz square and minus sz. Now let us go to the next question. Suppose you have a 1D ferromagnet means D is greater than 0 for a 3-pin system with boundary conditions. What is the partition function of the system? So again, this is a very similar question. You have to enumerate all the spins and then calculate the partition function. So let us do that. So all you have to do is sigma sigma 1, sigma 2 and sigma 3 and 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Then it is 1 1 minus 1 minus 1, 1 1 minus 1 minus 1. Then it is 1 1 1 1 minus 1 minus 1 minus 1 minus 1. Then what you have to, so what is H? This minus J, 3 spin system with periodic boundary condition. So it is sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Okay, now what would be the value of this energy? So it will be here minus 3J. Okay, similarly here also it will be, see, minus 3J you will get here. And like if you see in rest of the case, you will get J J J J J J. So 1 2 3 4 5 6. So your energy will be e to the power minus beta h will be e to the power 3 beta j and e to the power beta j, and this also you will get e to the power 3 beta j and e to the power . So e to the power minus beta j, e to the power minus beta j, and so on and on. So up to 6 values, 1 2 3 4 5 6. So it will be 6 times e to the power minus beta j. This is the partition function, and this will be 2 times e to the power 3 beta j, one this and one, so one this term and one this term. So this is your correct expression. Now let us go. So this was the some of the questions of the previous assignment 9. Now let us look at some of the previous year questions. So which of the following is true for a superconducting state? A superconductor in the superconducting state exhibits perfect diamagnetism. So this effect is called Meissner effect, and this statement is true. This is a true statement. The entropy in a superconducting state is perfect diamagnetism. Yeah, so the entropy in a superconducting state is higher than in a normal state. So this statement is not correct. Why? Because in a superconducting state, the entropy is lower than its normal state. So what happens is, so this statement is correct. Yeah, so the correct statement is the entropy of a superconducting state is actually lower than the normal state. So at the critical temperature, so this has been experimentally determined, and it turns out to be Tc is directly proportional to the square root of the isotopic mass. So inversely proportional to m, this is a wrong statement. Now the relative permeability, so what is relative permeability? It is 1 plus chi. Chi is the magnetic susceptibility. Now since chi is minus 1, so since chi is equal to minus 1, mu has to be 1 plus minus 1 is equal to 0. So permeability cannot be 1, relative perm cannot be 1, so it is wrong. And like if you ask why this, because like the Masnier effect, it tells that the field inside the superconductor has to be 0. So we have this mu naught h plus m, right? So what would happen if so the way it has to happen is mu naught h, and from the definition of the susceptibility, m can be written as chi times h. So it is mu naught 1 plus chi h. So to satisfy the Masnier effect, this has to be, the magnetic field has to be 0, and this can be 0 if 1 plus chi is equal to 0. So chi is equal to minus 1. Okay, so these things come from Masnier effect. Okay, so the correct answer is the first option. Now the second question, which of the following is not true about Mermin-Wagner theorem regarding spontaneous order? So let me tell you what the statement, what the theorem states. So the Mermin-Wagner theorem states that continuous symmetries cannot be spontaneously broken at finite temperatures. In systems with short range interactions in dimensions less than or equal to 2. So, and this theorem doesn't apply to this theorem doesn't apply to discrete symmetries. Okay, so this statement is like in the first, and so this theorem does not apply to discrete symmetries. So it only applies to the continuous symmetries. So this statement is wrong, or which is not true. I mean, this is your answer basically. So it applies to continuous symmetry but not to discrete symmetries. So this statement is true. The continuous symmetries cannot be spontaneously broken at finite temperature in. So this is what the statement of the Mermin-Wigner theorem. The continuous symmetries cannot be spontaneously broken at finite temperatures in systems with sufficiently short range interactions in dimensions d less than or equal to 2. So this is correct. Okay. Now we go to the next question. Which of the following is true for magnons in a ferromagnet? So if you calculate the dispersion relation of magnons in a ferromagnet, so you will end up with an expression like this. So the dispersion relation for magnons, so it turns out to be h bar omega is equal to 2js. S is the spin, j is the constant in that Hamiltonian which determine if it is a ferromagnet. So j positive means it is a ferromagnet. So 1 minus cos k a. Okay. So this is the dispersion relation we will end up with. And if you, so what we have to do at long wavelengths, okay, magnons are fermions and hence, so this statement is wrong because magnons are bosons. Magnons are bosons. So then we have to check this. At long wavelengths the frequency is proportional to k square, or at long wavelength the frequency is proportional to k. So to check that, so we have to just expand. Long wavelength means what? So k is equal to 2 pi by lambda. If lambda is long, k goes to 0. This is the long wavelength limit. Okay. So if k goes to 0, so we can expand this around 0. So it will be 2js 1 minus. So this will be 1 plus k square a square over 2 factorial. 1 minus 2 factorial plus higher order terms that will neglect. So what we'll have is 2js 1 minus 1 plus k square a square by 2. So 1 minus 1 is 0. So here we directly see omega is directly proportional to k square at long wavelengths, at k greater than 0 or lambda goes to infinity, or long wavelength limit. So your correct answer is this one. At long the frequency proportional to k. This we just found that it is not true. Okay, so this is true for magnons in a ferromagnet. Let us now go to the next question. Which of the following is correct statement regarding the Meissonier effect? Okay, the outcome of application of a magnetic field is history independent for both superconductors and perfect conductors. Okay, so this statement is wrong, because for a perfect conductor it is dependent on history. Okay, but for a superconductor what the Meissonier effect says is that the field inside, if the field is always expelled out in a superconductor, so it irrespective of there was field before or not. So what we learn from here is that So this is Meissonier effect. This is history independent. So irrespective of suppose if you do an experiment, so you have this uh, superconducting sphere, and you put it in some magnetic field, uh, then the fields will get expelled out. And you so what you can do is, so the experiment is this: you have this, and then you cool. So you have this, you apply the field, and then if you just cool it below the superconductor, or that get the temperature less than Tc, you will get this. The fields will be expelled out. Or you have this, you first cool it, and then you apply field. What you have is this, the same situation. Okay, there will be no field inside, no magnetic field can be inside here. But here in the case of perfect conductor, what you have is, so this also you can easily prove. So if you have a perfect conductor, you first apply field, and so let us say you are applying this field, and then you cool it. So what you will have finally is, you will still have this, the magnetic field will remain constant when you cool it sufficiently to 0. And here if you first cool and then apply field, then what would happen is, the no field can penetrate inside now. Because what happens is, if you just cool it to so perfect conductor means what, rho is equal to 0. So if you cool it so much so that the rho has become 0, there will be no change in this magnetic field inside the, so whatever the field there was before the cooling, that the same field will get freezed after the cooling as well. So this you can see is that this is dependent on the history, but this is independent of the history. So this thing is history dependent. So it is history independent for superconductors, but not for perfect conductors. This is correct. The outcome of application of history in, so this for both it is not correct, and independent for perfect, so this statement is wrong. It is not history dependent for perfect conductors. So your correct answer is option number 3. Now let us go to the next question. The critical temperature of mercury with isotopic mass, so critical temperature has been given, Tc is equal to 4.185 Kelvin. For the isotopic mass, M is equal to, let's say this is Tc1, M1 is equal to 199.5 some atomic mass unit, and the critical temperature of the mass, if its mass changes to, so this we have to find, and if the mass changes to 203.4 AMU, so what we have is, we know that the critical temperature is inversely proportional to the square root of the isotopic mass. So what we can write this as, Tc2 is what we need to find, Tc1 is equal to M1 over M2, and we have to take the square root of that. So this implies that Tc2 is equal to Tc1, and this will be m1 over m2. So what we have is Tc1 is 4.185, m1 is 199.5 divided by m2 is 203.4, and we have to take the square root of that. So whatever the value you will get from here, that is your that would be your the critical temperature if its mass change. So let us quickly calculate that. So it turns out to be 4.185 into square root of 199.5 divided by 203.4. It comes out to be 4.145, around 4.14. So we see that the temperature is reduced. That is because the mass has increased, and because of this inverse the critical temperature is inversely proportional to the square root of isotopic mass. Okay, so which of the following statements is not true for type 1 and type 2 superconductor? The type 1 superconductor totally excludes the magnetic flux, while the type 2 superconductor partially admits magnetic flux. So this statement is true. The type 1 superconductor is a perfect diamagnet, and type 2 superconductor, so it can admit some flux in as some vortex. Okay, so that statement is true. Type 2 superconductor has two critical fields, while type 1 has only one. So this statement is also true. If you look at the field plots, so it will look like this, something like this. So this is one critical field, this is another critical field. So it's C1, it's C2. Okay, so xi is greater than square root of 2. So this lambda is the penetration depth, and chi is the coherence length for type 1 superconductor. And okay, let's see, type 1 superconductor show a vortex state. This statement is wrong. Only in type 2 superconductors so the correct statement is type 1 are perfect diamagnet, and type 2 they exhibit vortex states where they can admit some magnetic field. So this statement is false or not true, and this is your correct answer. So this coherence length is greater than square root 2 times. So this is true, and type 2 has two critical fields. This is also true. Now let us go to the next part, the isotope effect in tin. The following data was obtained for dependence of the critical temperature Tc on tin on its average atomic mass. Okay, so these are the atomic mass is given, and these are the critical temperature. So if on the x-axis 1 by square root m is plotted, so 1 by square root m is plotted, and TC is on the y-axis. So this is TC, this is TC. Which of the following curve is correct representation of the data mentioned in this? So we know that TC is directly proportional to 1 by square root of m. So TC will be some constant k times square root of m. So, and this would look like this if you plot here square root m and this is t. So the correct answer is, it is only B only. Okay, so this looks like correct, but it is increasing. So that is why B is the correct answer. Let us go to the next question now. Which one of the following statements regarding superconductors is false? Okay, the magnetic field enters in form of fluxes inside type 1 superconductor. So this statement is clearly false because type 1 superconductor are perfect diamagnet. Perfect diamagnet. But in type 2 superconductors, the fields can penetrate as vortex states. So this statement is false. Okay. So the London's equation is given by, yeah, so this is correct. This is how the London's equation is obtained. Yeah, so all these three are the correct statements. We can understand it by, we can simply try to go through it. Just give you some outline of how we can get this. So we have this, the current is given by minus E and Vs. Vs is the velocity of the superconducting electrons. Okay, so this we have, and we have from the Drude equation m dVs over dt is equal to E A. Okay, so what we have is, if you take the time derivative of this, so dj over dt is equal to minus E and Vs and the time derivative of that. So this, from here what we get is dVs over dt is equal to E over m. So that we can write minus E and this is E by m. So minus n E square E over m. So that's the E will have this minus sign. So it is okay. So now what we are going to do, so dj over dt is equal to n E square over m E. Now we take curl on both sides and use curl of E is equal to minus 1 by C del T of the magnetic field. So you take curl on both sides. So what you get is, so del T curl of J is equal to n E square over m. Now curl of E is equal to minus 1 by C minus 1 by C del T of B. So what you have here is curl of J is equal to minus n E square over mc B. So actually it is the time derivative of this. So what you get is this. So if you just rearrange, this is equal to 0. So for the London's equation, what you need to do is you have to choose. So what it means is that the curl of J plus n e square over mc times b for the London, so that has to be a constant, and out of those many constants you have to choose that constant has to be 0. So for London equation, that constant you need is plus n e square over mc b. That constant you need to choose is 0 for London's equation. Okay, so this statement is correct. Now what you can do is you can write so let us verify if this is true or not. So here b you can replace as b, you can write as curl of a, and j is equal to minus n e v, and that you know v is equal to, so m by m, so mv minus n e p over m. Okay, you put both this here, so it is curl of, so I'll write so what we have is curl of j, instead of j we are writing minus n e p by m plus n e square over mc and curl of a is equal to 0. Okay, now we can cancel one n e m and we are left with a by c. So from here what we can get is p minus e a by c is equal to 0. So this p is actually the average p. So yeah, so this is consistent with this. So this statement is correct, and you can find the London penetration depth lambda L square is the distance over which the external magnetic field is screened out inside. Yeah, so this statement is also correct. So to see that, what you have to do is you have to use the Ampere's law. So how do you use Ampere's law is so curl of B is equal to four pi by c times j. Okay. Then you have to take curl on both sides. So I'll just do it once. So we know that 4 pi by c j is equal to curl of B. So take curl on both sides. So what you have is 4 pi by c curl of j is equal to curl of b. What is so this will give you this del square b. So this vanishes because of the divergence theorem, and so you are left with only minus del square b. Okay, and this curl of j, now you can use the London's equation 4 pi by c, and from London's equation what you have is curl this is minus n square mc b, n square over mc into b. So this is minus n square over mc times b is equal to minus del square b. Okay, so del square b is equal to 4 pi over mc square n square to b. So here you see this has a unit of 1 over r square, so we can write as 1 over lambda square b. So lambda is nothing but mc square over 4 pi n square root under of that. So this is your penetration depth. So, or basically here lambda square is equal to mc square over 4 pi n square. So this statement is also correct. Which one of the following statements is correct when a material undergoes a transition from its normal state to its superconducting state? So the Cooper pairs lose their ability to transfer energy to the lattice. So this statement is upon the formation of the superconducting, the lattice becomes surface. So this statement is false. The Cooper pairs lose their ability to transfer energy to the lattice. So why this is false? So how this Cooper pair forms is there will be an electron and the lattice, it will attract the lattice points to create, so this will attract the lattice points, and so when this lattice points would be like mostly positive charge, because each of the lattice points would be giving out some electrons, and this electron then runs away, but it will take some time for this so it will, these are now closer as opposed to all this. So there will be local positive charge, and in that local positive charge the other moving electron that will come and get stored. So the electron which went away, that can again create the similar effect and transfer its energy to the lattice. So this statement is the Cooper pairs lose their ability to transfer energy to the lattice. This is wrong. This is false. Upon the formation of a superconducting state, the lattice becomes less efficient in heat transfer. So it is just the heat transfer occurred through the phonon modes. So when the phonon modes, when they there is a reduction in thermal conductivity. So the phonons can still the phonon dispersion relation, it remains intact. So this statement is false. It is same. The lattice becomes less efficient. So this the efficiency of heat transfer, the thermal conductivity, it doesn't sorry. So the thermal conductivity will reduce, that is for sure. This is a true statement. The lattice less heat transfer. Electrons in normal state lose their ability to transfer heat because coupling to the pairs. So the normal state electrons, they will not lose any ability to transfer heat. So this statement is wrong. The normal state electrons, that will behave as previously only, just before the formation of the superconducting state. The formation of, so this statement is also wrong. The lattice doesn't reduce its capability to transfer heat. It is the electrons which participate particularly in the Cooper pair. Because of that, the thermal conductivity will reduce. So in a superconducting ring carries a steady current in presence of a magnetic field normal to the plane of the ring. Identify the incorrect statement. So we have a ring and some magnetic field is passed through it. So because there is a magnetic field, the flux passing through the super is quantized in terms of H over E. So this statement is wrong. This if you do the quantization, it turns out to be H over 2E actually. So this is wrong. The current and magnetic field are time independent. The current and magnetic field in the superconductor are time independent. Yes, this is true, because if you try to remove the external field, so initially you put this magnetic field, there would be some current set up here. Now you cool this to the superconducting state, that current will still try to flow and that magnetic field will try to be maintained. So in the superconducting state, it is time independent and it stays for a very long time, where lambda is a constant. So this is London's equation. So this is true. The supercurrent doesn't decay over a long time. So this is also a true statement. So because it is time independent, it tries to stay as it is for a very long time. So these are all for today's discussion. I hope you got so you are understanding the discussions over here. If you have any questions, you can ask me.